In this next subsection, we're going to be looking at how to calculate confidence limits for a single population mean when the population standard deviation sigma is unknown. So let x bar, s squared, and s denote the mean, variance, and standard deviation, respectively, of a random sample of size n from a normal distribution with mean mu and variance sigma squared. Now, we're assuming that both mu and sigma squared are unknown, and so in order to make inferences about mu, with sigma squared being unknown, we'll have to estimate sigma squared, and that's going to cause us to use the t-distribution as we did in the case of hypothesis testing. So since the random variable, denoted by t, which is this studentized version of x bar rather than standardization, studentization, so x bar minus mu, and we divide that difference by the estimated standard error of x bar, so the sample standard deviation divided by the square root of the sample size. We know, based on what we've looked at previously, that this random variable has students' t-distribution with n-1 degrees of freedom. And so because of that, and because of the definition of this upper alpha percentage point of the t-distribution with n-1 degrees of freedom, we know that the probability that this t-value, this t random variable, is less than or equal to the upper alpha percentage point of a t-distribution with n-1 degrees of freedom. We know that that probability is 1 minus alpha. And so that implies then that the probability that this expanded version of t, so x bar minus mu over the standard deviation divided by the square root of the sample size, is less than or equal to that upper alpha percentage point. That's also 1 minus alpha. And then we can rearrange the stuff here inside the parentheses to get mu on one side of the inequality all by itself. And so just doing a little bit of algebra, that corresponds to the event that x bar minus this t value times s over the square root of the sample size being less than or equal to mu, that probability is 1 minus alpha. So again, let's think carefully about what this is saying. Remember that whenever we have a probability statement, there's always at least one random variable in the expression or in the event whose probability we're trying to find. And so in this case, we actually have two random variables, x bar and s. So the left side here, the left side of this inequality is a random variable. It's a combination of x bar and s. And so what we're saying is that the probability we get a hold of a sample for which the sample mean x bar and the sample standard deviation s are such that this combination of x bar and s, so x bar minus t times s over the square root of the sample size, that is less than or equal to the population mean, mu, that probability is 1 minus alpha. So another way to say this would be that the probability that mu is greater than or equal to this random variable is 1 minus alpha. So if we think in terms of the relative frequency definition of probability, this implies then that in repeated sampling, the random variable x bar minus t times s over the square root of the sample size will be less than or equal to the mean mu 1 minus alpha times 100% of the time. Another way to say that is that the mean will be greater than or equal to that random variable 1 minus alpha times 100% of the time. And for that reason, we call this random variable a 1 minus alpha times 100% lower confidence limit for mu. So this is very, very similar to when we assumed that we knew the population standard deviation sigma. The only difference here now is that we don't know sigma, so we're having to estimate it using the sample standard deviation. And this interval coefficient that we're using does not come from the standard normal table, but from the t-table. But that's really the only difference. Overall, the idea is exactly the same. Now, once we have a sample, once we've calculated this random variable, this lower confidence limit for mu, then the way that we say this is that we are 1 minus alpha times 100% confident that mu is greater than or equal to this lower confidence limit. We also have, using the same kind of argument, we have that the probability that the population mean mu is less than or equal to this random variable, so x bar plus t times s over the square root of the sample size, that probability is 1 minus alpha. And so that implies that in repeated sampling, x bar plus t times s over the square root of the sample size will be greater than or equal to the mean mu 1 minus alpha times 100% of the time. Another way to say that is that the mean will be less than or equal to that random variable 1 minus alpha times 100% of the time. And so because of that, for that reason, the random variable x bar plus t times s over the square root of the sample size is called a 1 minus alpha times 100% upper confidence limit for mu. And then once we have a sample, once we've calculated x bar and the sample standard deviation and plugged them into a formula like this, then we say that we are 1 minus alpha times 100% confident that the population mean mu is less than or equal to this upper confidence limit. And then if we compute a 1 minus alpha over 2 times 100% lower confidence limit using an analogous formula from a couple slides ago, and a 1 minus alpha over 2 times 100% upper confidence limit for mu, all right, which we looked at on the previous slide. And if we put those two confidence limits together, then we obtain a 1 minus alpha times 100% two-sided confidence interval for the mean mu, all right? And so again, this is analogous to what we did when we assumed that we knew the population standard deviation. Now, though, it's the more realistic scenario where we don't pretend that we know sigma, all right? Sigma is considered to be unknown, and so we estimate it using the data through the sample standard deviation. And in order to do this, we have to get our interval coefficients from the t-distribution rather than the standard normal. And so putting these results together, we have the formula for a 1 minus alpha times 100% lower confidence limit for mu. We have a formula for the 1 minus alpha times 100% upper confidence limit for mu. And then we have the formulas for the endpoints of a 1 minus alpha times 100% two-sided confidence interval for mu. Okay, let's look at an example. Again, we're continuing on this example with the peanuts in jars. So recall example 4.2, in which a company that packages salted peanuts in 8-ounce jars is interested in maintaining control on the amount of peanuts put into jars by one of its machines. So what we're going to do here is construct and interpret essentially what we're really after here, ultimately, is a 95% two-sided confidence interval for mu, and then to draw an inference based on that. To get there, and again, just to demonstrate that if you construct the appropriate lower and upper confidence limits individually and put them together, you will get the appropriate confidence interval. That's what I'm showing here. So if we construct a 97.5% lower confidence limit individually and a 97.5% upper confidence limit individually, and if we put those together, then together they comprise a 95% two-sided confidence interval for mu. Okay, so the sample mean we calculated to be, from that data set, 7.8925 ounces. We calculated the sample standard deviation to be 0.1782 ounces. The sample size was 16, and so we have 16 minus 1, or 15 degrees of freedom associated with the sampling distribution of t. And we're going to first calculate a lower confidence limit for mu, and in particular a 97.5% lower confidence limit for mu. And so we need the upper 2.5 percentage point of the t-distribution with 15 degrees of freedom. And that value is 2.1314. We looked that up previously, so we don't need to look it up again. And so now we calculate via this formula here the value of that lower confidence limit, and we find that we get a lower confidence limit of 7.796. So we could say that we are 97.5% confident that the true mean weight of peanuts being dispensed by the machine is greater than or equal to 7.796 ounces. The upper 97.5% confidence limit for mu is obtained using this formula, so the only difference between the two is we're adding here. All right, and so if we do that, we get an upper confidence limit of 7.987. So we could say, if we were only using this upper confidence limit, we would say that we are 97.5% confident that the average weight of peanuts being dispensed by the machine is less than or equal to 7.987 ounces. Now, we want a two-sided confidence interval because we're looking not only for underfilling on average, but also overfilling on average. And so if we were to use that third formula on the summary slide for the confidence limit, x bar minus plus our t-value times s over the square root of the sample size, and using this for a 95% confidence interval for mu, right, the interval coefficient would be the upper 2.5 percentage point of the t-distribution with 15 degrees of freedom, and we found that t-value to be 2.1314. And so we would get endpoints, a lower endpoint, 7.796 and 7.987. And so we would say that we are 95% confident that the true average weight of peanuts being dispensed, which is mu, is somewhere between 7.796 ounces and 7.987 ounces. Now, a couple things to point out. We're using this formula for a two-sided confidence interval, and these are the endpoints that we get. And again, the reason we did the work on the previous page, I just wanted to show you that if you calculate 97.5% endpoints individually, the lower endpoint individually and the upper endpoint individually, you get the same values as if you use the two-sided confidence interval formula at not a 97.5 but a 95% confidence level. Okay, so let's also think about this in the context of the hypothesis test that we had performed previously. If you'll remember, the null hypothesis was that mu was equal to 8 ounces, and the alternative hypothesis was that mu is different than 8 ounces. So that's equivalent to our assuming that the process, the machine, is in control, and we're going to let the data try to convince us otherwise. In other words, we're going to let the data try to convince us that the mean is different than 8 ounces. Now, if you think back to the last topic that we looked at in the context, or in Module 3, we talked about the correspondence between hypothesis tests and confidence intervals. And this is another example of that correspondence. So let's suppose that we had not done the hypothesis test. Let's suppose that all we had so far was this confidence interval, this two-sided confidence interval. Then because the 95% confidence interval, which ranges from 7.796 up to 7.987, since that confidence interval does not contain 8 ounces, then we could conclude based on this confidence interval alone, without actually going through the mechanics of the hypothesis test, we know that we would reject the null hypothesis that mu is equal to 8 ounces at the 5% significance level. Okay, so that 5% is obtained by subtracting 0.95, which corresponds to this confidence level, from 1. And so because the hypothesized value under the null hypothesis, 8 ounces, is not in this confidence interval, we know that were we to do the hypothesis test, we would reject that null hypothesis. So this is, again, showing this correspondence between hypothesis tests and confidence interval estimates. Now, in addition to being able to make that qualitative decision whether to reject the null hypothesis or not, which in this case we would, above and beyond that, we actually have a range of values that we have high confidence that mean actually is within. So we actually have more information using this confidence interval than we do with that hypothesis test, because we not only can make a qualitative decision about whether to reject the null hypothesis that the mean is equal to 8 ounces, but we have this range of values that we have high confidence that the mean is actually contained within. What if instead of a 95% confidence interval, we were to construct a 99% confidence interval? Well, let's do it. The endpoints are given by x bar minus plus the upper 0.5 percentage point of the t-distribution with 15 degrees of freedom, so the right tail area would be 0.005, times the sample standard deviation over the square root of the sample size. And this t-value is 2.9467. If I were to bring up the t-table here, let's see here, so we have 15 degrees of freedom, and we're looking in this column for 0.005, and so we would get to 3 decimal places 2.947. So again, And when I look this up, I'm using a different table, right? But if we round this to 3 decimal places, we get exactly the same value. And when we do the calculation, the lower endpoint is 7.7612. Right here, the upper endpoint is 8.0238. So that's right there. And so we would conclude then that we're 99% confident that the average weight of peanuts being dispensed is between 7.7612 ounces and 8.0238 ounces. Now notice that for the 99% confidence interval, 8 is actually in this interval. And so if we were to use this interval instead of doing a full-blown hypothesis test, if we were to just use this confidence interval to draw a conclusion, we would get draw the same conclusion that we did when we used a 0.01 level of significance. Since 8 is in this interval, then we know that we would fail to reject the null hypothesis that mu is equal to 8 at the 1% significance level. And that's exactly the conclusion that we drew when we did the hypothesis test at the 0.01 level. But not only can we make that qualitative decision, we're actually quantifying the range of values that we're 99% confident that the mean is within. So with confidence intervals, we see that we can answer the same kinds of questions that we can with hypothesis tests, but we also get more information in the sense that we get the range of values within which we have high confidence the parameter resides. Okay, now let's think again about the example 4.3 involving the apple buyer. And remember that the apple buyer was trying to make an inference about whether he or she should pay the premium. They would pay the premium if the average diameter of the apples in the entire shipment exceeded 2.5 inches. The null hypothesis is that the average diameter of the apples in the entire shipment is less than or equal to 2.5 inches, and the alternative hypothesis is that the mean is greater than 2.5 inches. With that in mind, let's think about the appropriate or the corresponding type of confidence interval or confidence limit to construct. Because we're trying to show that mu is greater than 2.5, in other words, that we're performing a right-tailed test, then the appropriate confidence limit to construct is a lower confidence limit. And if we wanted a lower confidence limit that was comparable to or that corresponded to that right-tailed test performed at a 5% significance level, then we would calculate a 95% lower confidence limit for mu. The formula for that is x bar minus the t-value, the upper fifth percentage point of the t-distribution with 11 degrees of freedom, times the sample standard deviation divided by the square root of the sample size. And so we already looked up that t-value before in the context of the hypothesis test. And so we just plug this in, and we get a lower confidence limit, a 95% lower confidence limit of 2.5539. And so what we would say then is that we are 95% confident that the true average diameter of the apples in the entire shipment is greater than or equal to 2.5539. Now, because that lower confidence limit of 2.5539 is greater than the hypothesized value in the null hypothesis, that 2.5, right, which is the upper endpoint of that interval comprising the null hypothesis, then we know that we would reject that null hypothesis in favor of the alternative and conclude that mu is greater than 2.5 inches at the 0.05 level of significance. So we're 95% confident that mu is greater than 2.5539. And if it's greater than or equal to 2.5539, then it's certainly greater than 2.5. So that would be the basis then for rejecting this null hypothesis in favor of the alternative at a 0.05 level of significance. Now, remember that we also, in the context of that hypothesis testing example, looked at, or we performed the test at the 1% significance level. And so a corresponding lower confidence limit would be a 99% lower confidence limit. And so let's do that. And so the t-value for that test was 2.7181, and that is the interval coefficient for this lower confidence limit. And so we get 2.4490. And so the conclusion that we would draw, the way that we would interpret this lower confidence limit, is that we are 99% confident that mu is greater than or equal to 2.449 inches. Now, that's just a little bit below 2.5. And so 2.5 is in the interval, the confidence interval for mu. And so based on this, we know that if we were to go ahead and test that test the hypothesis at a 0.01 level of significance, we would fail to reject the null hypothesis at the 1% level of significance. And that's the exact conclusion that we drew when we tested the hypothesis at the 0.01 level. So again, we're seeing this correspondence between a hypothesis test and the corresponding type of confidence interval. Now, a picture that summarizes what we just did in constructing a 95% lower confidence limit for mu and a 99% lower confidence limit for mu is shown on this page here. So here I've got that part of the number line where mu can reside, and this 2.5 right here, this was the threshold that we were looking for. If the average diameter of the apples in the shipment exceeds 2.5 inches, then the buyer would pay the premium. And so when we constructed a 95% lower confidence limit for mu, that lower confidence limit was 2.5539 right here. And so we are 95% confident that mu is somewhere out here. Well, every point in that interval is greater than 2.5. So again, based on this lower confidence limit, we know that we would reject that null hypothesis that mu is less than or equal to 2.5 in favor of the alternative which says that mu is greater than 2.5, and we would draw that conclusion at the 5% significance level. On the other hand, because the 99% lower confidence limit for mu is just a skosh below 2.5, so 2.5 is in this interval of possible or plausible values, right? We say that we're 99% confident that the mean diameter of the apples is greater than or equal to this 2.449. And so we cannot rule out values that are less than 2.5 as being the true values. So we can't rule those out. And so thinking in terms of the hypothesis test, we know that we would fail to reject that null hypothesis that mu is less than or equal to 2.5 at the 0.01 level of significance. So that wraps up constructing confidence limits for a population mean where we don't know the population standard deviation and therefore are using the t-distribution.